Hi, my name is Scott Riley. I'm a postdoctoral researcher here in the Materials Science and Engineering Department within the Advanced Materials Laboratory, working with Dr. Brian Jacobus. My research focus is on alternative ceramic nuclear fuels. And specifically this summer, what I'm going to be doing is looking at specifically the kinetics for the synthesis of these alternative fuels using a piece of equipment called an STA, or Simultaneous Thermal Analysis Unit. And within this system, I'm able to measure the change in mass of my material as a function of temperature, but also how the energy in the system changes. And based on those two pieces of data, I can back out the reaction kinetics.
Hi, I'm Tyler Swartz. I'm an undergrad student here in the lab as part of the REU this summer. This summer, my project is working on understanding the reaction kinetics of converting dysprosium oxide into dysprosium nitride, which serves as a surrogate study for nuclear fuels.
Hello, my name is Nathan, and I am a GeoFP fellow and also a first-year graduate student here in the Advanced Materials Lab. And currently, I'm preparing to conduct my research project on the positive uranium nitride in advanced nuclear fuels. My research project will help to advance nuclear fuel technology, which will improve the safety and performance of nuclear power reactors, specifically those intended for space-based applications.
Hi, my name is Primrose Bomokai, and I'm working on hexagonal boron nitride coatings for these sensors operating in extreme environments. So for my coating, I use the materials and use the specs mixer to mix the materials and the powders. I place the powders in the vial, and with the balls that will be working to mechanically grind the powders and then reduce them. Then I load it into the specs mixer, which is a high energy mixer, and it helps in mixing of the powders.
Hello, my name is Hector Ramirez, and I'm part of the inks team here in the AML. Our research looks at hexagonal boron nitride coatings that will be used on sensors in extreme environments. This is important because we want our sensors and electrical components to have protective barriers that will protect them from irradiation, high temperatures, and it's just important so that these sensors function properly and have long lifespans in things like nuclear reactors or aerospace applications.
Hi, my name is Jacob Olson, and I am a first-year graduate research assistant in the Advanced Materials Laboratory. To piggyback off what Hector and Prim just talked about, they are on the printing side of this project, and I'm on the sintering and characterization. So the first step that we do for the heat treatment of these prints is we want to get all the organics out, all the things that aren't hexagonal boron nitride, and we do that in this tube furnace right here. We want to take it up to about 600 degrees Celsius and burn out all those other products in it and decompose them, so that we just have a ceramic only print. And then after we're done in the tube furnace, we move our prints over to the tungsten furnace over here, which is this big one. And this one, tungsten, it has the highest melting temperature of any element. What we do here is we just want further densification and consolidation of those ceramic only prints so that we can achieve the target properties of thermal conduction, electrical insulation, and corrosion resistance like they talked about in the videos.